Okay, so I took a look at the problems in chapter 16, and what can I say? There are a tremendous number of them, but this is a little bit misleading because it's not the case that I'm going to give you like all of these problems to do for homework or something, and this one chapter is going to have an abundance of problems. Upon closer inspection of the section of the problems, what I'm realizing is that in a longer course in group theory, each of these sections would likely be like a chapter of the class. There are a lot of really important theorems that he puts into the exercises here, and we're just not going to have time to look at a lot of them. So I've selected some of them like from the what I would call the normal exercises of this chapter for our homework, and similarly for us to go through in the problem portion of these videos. And what can I say? If this was an in class, then what I would do is instead of probably final exams, because no one likes exams, we would probably do projects and presentations. And then I would use those and other theorems that you might find in a book, like this guy, very large book, as you can see. And I would find, problems and theorems that would make for good presentations for you to go through. And I think, therefore, someone who is looking to practice their group theory skills and really get to the next level would be well served by taking a crack at some of these. And in our homework, I point out which of them I think are really good for that. But most of the exercises in this chapter kind of fall into this category of extending your group theory knowledge even further and really taking it to the next level rather than the more routine exercises. That out of the way, I've still picked some of them that I think are good to show. And so the first one I want to show is problem A5, which deals with the fundamental homomorphism theorem, and in particular, applying it in a certain case. So in all of the problems in section A, we're going to use the fundamental homomorphism theorem to prove that two groups are isomorphic. And in this particular example, the two groups that are given are a Z mod 3Z and Z mod 3Z cross Z mod 3Z. Obviously, those are not isomorphic. Modulo the group K, where K is in particular, let me just make sure I'm using Pinter's notation. He just writes down the elements explicitly as three ordered pairs. And this is often known as the diagonal subgroup. And in general, if you have any group G, you can form G cross G. And the diagonal subgroup is often called this, delta G, which is a subgroup of G cross G equal to the elements of the form G comma G. I think we've encountered this in the homework before, actually, so maybe I didn't have to explain that. In any case, the way that we go about applying this fundamental homomorphism theorem is given two groups, the one with the quotient group, what I do is I make a map from G1 to G2, whose kernel equals the thing that we quotient by. And then the fundamental homomorphism theorem says I also have this natural quotient map to G1 mod K. And the theorem says, here is my isomorphism, which we talked about in the videos. There will be an isomorphism between them. So what I have to do is, given the group with the quotient, I need to find a function. Let's spell this out explicitly in this case. From Z3 cross Z3 to Z3, whose kernel is exactly the diagonal. So when you have to do this, what we'd like to do is we're kind of basically reverse engineer, right? I need to find a function, which is a homomorphism, and it's zero exactly when you plug in two things that are the same. So in some sense, it has to be sort of symmetric, or maybe a better way of saying it would be anti-symmetric, so that when I plug in two things that are the same, it cancels out to zero. And the simplest function I know that is antisymmetric and gives you 0 would be phi of AB equals A minus B. That seems like a very reasonable guess then. So now what I have to do is see that this is a homomorphism and its kernel is the thing that I want it to be. That part is easy, right? The kernel of phi is when phi of AB equals 0. And of course, if I set this equal to 0, then A is equal to B. So yeah, very, very straightforward. There's maybe the world's tiniest bit of checking that one could do if one was really skeptical about equivalence classes and such, making sure that it's well defined, but this is very straightforward. I think at this point we have a lot of experience with modular arithmetic. I think you guys agree that this works. So what I have to do now is check that this is actually a homomorphism. So what would that entail? I would need phi of AB plus CD to be phi of AB plus phi of CD. One remark is I'm going to immediately stop writing the extra parentheses. Here I didn't do it. I just treated it as a function of the two arguments. Here, I'm thinking of AB as an element of this ordered pair, just for the sake of emphasizing what the equation shows. But really, it's completely fine to just write phi of AB. We're not computers. We don't throw syntax errors when we're missing extra parentheses. You guys get the point. I just wrote it that way just to really emphasize what the homomorphism equation is saying. So what this would do is this thing sends it to, right? We know how to add these things. So this becomes A plus C, B plus D. And this is A plus C minus B plus D. There really isn't any better way of writing it. It's kind of fully simplified as it is. Whereas this side is A minus B, and this side is C minus D. And now that we're in one group, I can just collect the terms here. So let me collect everything. And we see that they are in fact equal. That makes this a homomorphism. We've checked the kernel already. So therefore, by the fundamental homomorphism theorem, I'll just write G mod K is isomorphic, maybe G1 mod K is isomorphic to G2, rather than write the whole thing out again. And we declare victory. Not so bad. So you guys have a couple like this that I picked out in the homework where the strategy is the same. You have some groups, you find the one that has the quotient involved in it, and you find a homomorphism with the desired properties, and then it follows from the theorem. All right, friends, you guys give it a go. Good luck.